So welcome everyone to our educational webinar. Thank you guys for joining. Today's webinar topic will be NX Algorithmic Modeling, Revolutionizing Design with Logic and Rules. I will be your host. My name is Mason Wu from AT Engineering. I am based off in the San Diego office. Very excited to be here today with Taylor Anderson from Siemens. He's a subject matter expert of the NX Algorithmic Modeling tool. So he'll be the presenter for today. Before we dive into the actual content, there are just some housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, you can type them into the chat, and we'll have Taylor answer them at the end of the presentation. You will also be able to ask him directly if you like, and we'll unmute you at the end. This webinar will be recorded and be available on our ATA website and on our YouTube channel later. So before I hand this to Taylor, I just want to give a quick overview of AT Engineering about who we are and how we might be able to support your need. All right, so most people recognize ATA as an engineering service company. That's about 80% of our business. Our core founders have been together for almost over 40 years and have experience supporting customers with high-value engineering services, primarily on test and analysis-driven design. Majority of our business are in the aerospace and defense industry. That's around 70%, but we also work on other industries, as you can see on the screen. About who we are, ATA is an employee-owned small business with a full-time staff just over 200 people. And most of us have an advanced engineering degree, as you can see on the screen. We have 9 national offices. We just opened 2 more in the US. And as I've mentioned before, we have years and years of experience focusing on design, analysis, and test. This includes everything from structural design, structural dynamics, thermal, vibroacoustics, CFD, and more. Test-wise, we are the leading independent modal test group in the US. We have lots of experience flying our team to the testing article and conducting ground vibration testing. So we have talked about the 80% of the ATA service business. Aside from that, this is how most of you joining the webinar today know about ATA. We are a Siemens VAR, value-added reseller, who not only sells the product, but also provides software support and training. We focus on products and solutions that we use, and primarily on design, analysis, and test. For example, NX is for a leading CAD software used for design, which is also what we're presenting today. PMAP and Star CCM Plus for simulations, and we also have Test, which is one of the Siemens. One of the Siemens partner in the US that can provide Siemens testing hardware and software. Because we sell what we use, our customer appreciate our familiarity of the tools, and it really shows in our hotline support. Every time you call our support hotline, you are speaking with a project engineer who actually have the software already open and use that every single day and understand the problem. In addition, we teach a variety of classes, primarily dealing with simulation. We made the Siemens training material for the Nastran software, and a lot of time when you want to take a class online with Siemens to find a Nastran to help improve Nastran skills, you will find it either in Denver or San Diego because we are the one teaching it, and that's 2 of the locations we teach the class. So this slide showcases the ATA Siemens partnership over the years. It all started with a company called SDRC, which developed a popular PLM tool called Ideas. And at the time, ATA was part of SDRC, which ATA stands for the Advanced Test and Analysis Division. And year of 2000, we spun off from SDRC, became ATA Engineering, continually focusing on delivering high-quality engineering services and test support to our customers. So after a series of acquisition, SDRC was acquired by Siemens, and the Ideas software was integrated with Unigraphics, which later became the well-known NX product. In 2007, because we used so many of the Siemens tools, Siemens asked if we were interested in becoming a Siemens partner to help support customers who needs assistance. So we accepted the offer and became one of the Siemens VAR. In 2016, our VAR business grew rapidly and we achieved Gold Partner status. Around the same time, Siemens acquired CD Adapco, which is the company who developed a famous CFD tool called Star CCM Plus. Because we use and love Star so much, in 2018, we became one of the Siemens partner to sell and support Star, and also achieving a platinum status. And in 2021, we became one of the first partner authorized to sell and support Siemens test and measurement hardware and software. And fast forwarding to today, we are still continually working and providing more training and free resources for our customers, like the NX webinar you see today. So we hope you enjoyed what we're doing. All right, so last slide before I hand it to Taylor. I want to encourage people to visit our ATA website. We have our hotline support information, which is one of the unique advantage getting your support, Siemens software support from ATA, and free resources, including past webinars, FEMAP APIs, white papers that you can download free. All right. With that being said, happy to introduce today's speaker, Taylor Anderson. He is a NX product manager since 2005, has over 25 years of experience using the Siemens tool, and he will be presenting all the fun things we can learn today. Take it away, Taylor.
All right. Thanks, Mason. Appreciate it. Okay. Let's dive in. Good to be with you today. I'm excited to talk about NX Algorithmic Modeling. This is a relatively new area for us. We originally introduced algorithmic modeling in NX 1953, which was not in the year 1953, but was just about 3 or 4 years ago. And we've steadily enhanced it since. But yeah, an exciting new opportunity inside NX here. So we'll talk a little bit about how this works, what it's good for, when you might choose to use it, how it works with regular NX modeling, and how those can work together there. And then I'd like to fairly quickly get into NX and just start showing you some practical uses for this, how to get started, and some example models. So with that, let's dive in. Algorithmic design. And we talk about that. There are a lot of things around us that are using this kind of algorithmic design today. You may not have known that this was how some of these things are made, but but a lot of these kinds of shapes that you see out there that are interesting patterns, repeating kinds of patterns, patterns that are varying slightly and in interesting ways out there are very often used or created using some of the algorithmic tools that are out there. This really started in the architecture and construction industry, and there's some fascinating examples of this. You think of some of the famous swimming venue in Beijing, for instance, with the bubbles and so forth, has an interesting organic pattern, and we'll see how we can create some of those kinds of things in NX. These days, you look at things like grills on cars, right? There's some very, very fun, interesting, varying patterns that you see going on in those kinds of situations. Inside cars as well, some interesting textures that you start to see. Some of these almost knurling looking kinds of patterns on the right, and diamond patterns and things there in the Bentley on the left. And at smaller details, as you start to look at speakers and speaker grills and again textures and so forth, you see these kinds of interesting, repeating, varying patterns that are more and more common in a lot of the aesthetic products these days. Some of these are quite functional as well. We work with some speaker manufacturers who are very interested in the patterns and in certain attributes of those patterns that they feel make a big difference in the performance of their products. So as we look at where you may consider using algorithmic modeling, there are a couple major things that you may think about there. Of course, as you've seen here, we have things like complex or unusual patterns out there. This is a good way to do it, right? NX patterning, as it says here, is a relatively powerful tool. We can do a lot of really, really cool mechanical patterns using the regular NX patterned features and patterned component kinds of operations out there. But as it says here, sometimes your vision can exceed what the out of the box tools can do, right? And so yeah, the algorithmic modeling is going to open up some fascinating new doors here to expand your creativity. Number two here is geometry, as it says here, that's driven by external data potentially, right, or math out there. And I'll show you this airfoil example down here at the bottom in a minute here. But yeah, we've got some ability here to, as part of a feature, read in, for instance, some external data and use that to start to generate geometry, or to code really some math. I say code, it's drag and drop block logic kinds of design here. To create again interesting shapes that may be more mathematically driven. So again, we'll see some examples of this here as we go through. Differences with traditional NX modeling. A couple of interesting things here. The really interesting attribute of this algorithmic modeling is lists, and lists are going to be able to expand the capability of what you can do here. As we look on the right, of course, the upper image there is our traditional part history and a part navigator, and there's one feature selected there, of course, and you see some parent and some child geometry there. The pink, of course, is highlighting some parent features up above, and those edge blends are dependent on that particular extrude in there, and we can see those dependencies, of course, in that kind of way. With algorithmic modeling, you're going to see this kind of block logic down below, and it's going to create a flow really from left to right, and you'll see those kind of dependencies as we move from left to right within the graph or within the rule here. Lists are, we'll talk more about those in just a bit, but conceptually what lists can do here is let us set up a list of inputs. We feed a list of inputs to a node, and we can start to create multiple objects in rapid succession there based on all of the values of the list. We can start to combine those in interesting ways, and again, we'll see some examples of this in just a minute. But this allows us to start to create, in particular, again, pattern kinds of geometry very rapidly, where we don't have to model each individual feature. Right, we can model really the set of numbers, or the sets of numbers, or the sequences of numbers that would need to go together to create a particular kind of geometry. And again, we'll look at this in practice here in just a minute. One more important, interesting thing about algorithmic modeling is that we're working at a little bit lower level as we do this. This is not building up a set of traditional NX modeling features as we do algorithmic modeling. We're working at a little lower level, closer down at the parasolid level here, operating on geometry directly. And as such, it's lighter weight, really, than the normal NX modeling features out there. The result of this algorithmic design will be one NX modeling feature, and we'll see that algorithmic feature live inside the part history, and we can see that here in this next slide, where you'll see this algorithmic feature number 5 in here, for instance, that has some parents. It's dependent on some geometry, a surface and a solid up above, and then we can continue to model, right, and work on the result of that down below here as we've subtracted it away and added some blends and so forth, right? So again, what we're really doing is giving you the ability to create your own feature here using this block logic. You don't have to write any code. You don't have to debug code that way. And we can create that using drag and drop, connect the dots kind of interactions inside NX out there. As it describes here, that feature that you're creating can have geometric inputs that you select as you instantiate this feature. You may have expressions, choose to have expressions drive it if you want to. And then again, the geometry that's created is a live part of your session, a live part of your NX model that will update associatively as the model history is replayed in various ways, right? We can include these inside feature templates as well. If you're familiar with feature templates, they're kind of the successor to user-defined features. These are a really, really powerful collection of not just modeling features now, but things like PMI and parameter tables and a variety of other NX modeling tools that can be packaged into a reusable chunk of design to put inside a model as feature templates. So yeah, we're excited about that. There are a bunch of modeling features that have expressions associated with them. Generally, those are always inputs, right, to things like extrudes and so forth. There are a few kinds of features that will output expressions. Those are generally things like measurements, where we'll select some geometry and the result is a number that comes out. At the moment, we've chosen not to have algorithmic features have numbers as outputs, just because there's a lot of potential to generate lots and lots of numbers in very dynamic ways, and that may not be the most useful thing to do here. So just that's one little limitation there, a caveat here as you think about algorithmic modeling. There's a bunch of out of the box patterns that we include with algorithmic modeling. Several of these are some kind of standard shapes there. You see triangular, rectangular, diamond, and hexagonal cells out there. Cells we'll see this again in demonstrations in just a minute, are really looking at kind of the perimeter around a shape. They also have a centroid point there in the cell that we can use for a variety of modeling things. We also have kind of the grid incarnations of these, and these really treat more the edges as independent edges that we can do some interesting things with in other cases. We talked a little bit about some of those organic shapes, and these Voronoi cells down below are some concepts around that. And these generally are created with some random points, for instance, either in 2D or in 3D. We can do these with 3D as well, kind of a volumetric Voronoi. But we'll create those points, and really those boundaries all represent kind of the midpoints, essentially the closest or the equidistant lines really between all of the adjacent sets of points out there. And so again, as you create random sets of points, distribute those in interesting ways, you get some very interesting boundary patterns down in here. And again, we can use those associatively in NX modeling to create some very interesting shapes. Kind of a soap bubble sort of effect here as you look at the results of those. Using these standard patterns as kind of a starting point is super common with algorithmic modeling. So you start to see some of these kinds of things out there. You see that kind of grill or vent up there in the aircraft up there that you're familiar with the seatbelt and the no smoking sign, right? That could start as a rectangular grid out there. These grids can be planar. These grids can follow non-planar things as well. The image right below that of an isogrid on a nozzle kind of shape. I'll show an example, really exactly of very close to this exact geometry here in just a minute, and we'll walk through how to build this one from scratch. Some of these others on the far right over there, you see a couple different aesthetic designs that were from a manufacturer in Europe. That you see some patterns that are kind of embossed in those bands going around a couple of cups there. That have some interesting effects as the effect kind of fades off to the top and bottom. That's again part of the algorithm that designs those particular ones. You see some knurling kinds of things and other designs here again that start with some of our standard patterns, and of course use a little bit more logic to make them interesting. So with that, let's jump into some demonstrations of these kinds of things, and I just want to look forward at the rest of my slides here and make sure, you know what, I'm going to run through just a couple more really quickly, and just so in the interest of time, we make sure we hit everything. In terms of input for algorithmic modeling, we have lots of nodes out here in the block logic as we create that for selecting objects. We'll be able to see that here in just a moment as well. Inputs from either expressions or attributes if we want to. Other interesting ones like colors and fonts and so forth, and then lots of ways to input parameters down here. And again, we'll see a bunch of this here as we do that. As you see here, we've got lots and lots of modeling nodes. These again are not exactly the same as the NX modeling features that you're used to, but these create very similar shapes, right? The concepts behind these of course, are analogous to the NX modeling features. Again, these are a little lower level, and as such are quite a bit faster in many cases, particularly when you're doing many dozens or hundreds or even thousands of these. We've had some interesting designs lately, actually working with ATA and a customer, where we had a speaker manufacturer making in the neighborhood of 18 to 20,000 holes all at once, and that's very doable, right? With this kind of thing. I'll show an example here in a minute with several hundred, and you can see kind of the performance of that. So yeah, lots of different kinds of things we're able to approach here. And then, as I mentioned, lists are a very important thing. And so there's a very rich set. This is really kind of the crux of algorithmic modeling here, a rich set of nodes from manipulating lists and interacting with those kinds of that aspect of the modeling. So lots and lots of content here. And so with that, let's jump over. And again, I'm going to hop into the demonstration part. And whoops, I double clicked. And let's jump into NX, take a look at some things. I want to start with a really simple example here. And this was a kind of a non-slip floor mat kind of design, right? So we've got here starting with a basic block, and we've rounded the corners of this and put kind of an extreme chamfer on this to put a little taper on the edge of this mat down there, for instance. And then what we want to do is put a pattern into this top surface here. And so it's really embossing it or adding it on top of this. So this algorithmic feature that comes next here is doing that. And then particularly here, we've chosen a very simple out-of-the-box hexagonal pattern here. And really what this is doing is using that top face there and using the UV parameterization of that top face to create this pattern. And then we'll take the solids that creates and unite those to the mat, and we have our mat done. Okay. Now that obviously is the high overview. If we look at this feature again, this feature, we can see that it has parent and child relationships inside the model. As we edit this feature, we'll see a dialog come up that looks like any other NX modeling dialog, right? That has some inputs and has the ability to show a result and so forth. And we can change the quantities of these counts of these cells kind of in U and V here, the grooves and so forth. Let me do this a little differently. I'm going to edit parameters here just so we can still see the grid. That's a little easier to see. These groove widths right now are 5 millimeters wide, and we could make that 20 or something like that, and have the model update and show us a slightly different incarnation of that same pattern, right? Or change the quantities of these, and we'll do that here in just a minute. We'll crank that up quite a bit and get a more interesting pattern going there. But let's look at how this is put together, right? Again, if we double click, the highlighted, the dark thing in NX here is usually, was always the double click action. So this is to edit this, roll it back. Edit parameters is leaving it in its current state, but letting us edit the parameters. And that's what we're doing just a second ago. For algorithmic features, this edit definition is a new one here. And this is going to show us the block logic, right? And get us into that editing environment. And so as we go to that edit definition here, we'll see a relatively simple graph on the top that's going to pop up right now. And we'll see the model down here on the bottom as we get into that environment. And we've got a library over here on the left of a whole bunch of nodes that we can interact with. We can browse through them this way and hunt through the tree if we know what we're looking for. But personally, I like to use the search here to get at things fastest. This is an autocomplete kind of thing. So if I start to type the word select, for instance, SEL, everything with an SEL and it comes up quickly, and I can see that. It's some of them in the name of the node or some in the description of the node and so forth. So a very quick search capability over on that side. In the rule here that we can see, there are really a couple of key things in here. And one is this hexagonal cell node right here. So again, if I wanted to look for a hex there, I could grab that and get either the cell or the grid, and I can double click that to drop that out into my palette there, for instance, right? That's how I would get one of those out into there. I've got a bunch of those inputs, that face and some numerical inputs that we see over here on the side. the quick way to populate that is to just come here. I can grab here that select face, for instance, and grab a select face node and bring that in there and connect it this way, right? Grab that and plug it into that and go select a face if I want to. But the faster way to do it, I can delete that, is really to right click here and say create inputs. And what this will do is just generate kind of all of those for me, right? Create that stack at the beginning, and those stay attached then as we start to move things around, right? Let me undo that there, and I just want to pull back and yeah, stepping back through there, undo and redo work nicely in here. And so we've got that connected up here. We've got our face selected out there. Again, some inputs for this, and we can change these inputs right here if we want to, and the model will update nicely. The other big one that's in here is this extrude over here on this side. And really what we're doing is taking those hexagonal cells. We can go and display the data for these and look a little closer at these, but these are, as you can see them highlighting out there, these are a curve that is the hex, right? For each of these, and each cell is a curve. We're taking these, this list of, how many are there? 23 of these. And we're sending all of those to an offset curve command, right? And so as we send it 23 curves to come in, we get 23 curves out that are these offset curves that again, we're starting to be able to do in batch. So this is the list kind of thing that's happening here, right? As we get this list of 23 curves, we can operate on all of those at the same time. And we've got a width here that's our 20 that we entered a minute ago. We're dividing that by 2 and kind of splitting that and sending it inward right here, right? So we end up with all of these offset inward. And then with those curves, those 23 curves that we've offset inward, we can go and extrude all of those all at once, right? So again, this ability to do things in kind of in batch or as a list of things is super, super powerful here. With the extrude, as you would expect, you have things here for directions and limits and so forth, the body type. And again, if we want to create all of those at once, we can do this and start to string things together. And then the last part of any algorithmic feature is the output. We choose which of the entities that we're creating here we're going to actually output into the modeling space out there. So for instance, here we've got a bunch of cells that are curves. We've got some offset curves and things like that. This is really kind of our construction geometry. We don't need to output this stuff, right? We can have this just be part of the processing. And the bodies in this case are the only thing that's going to the output. So these solid hexes out here are the only thing that are the results of this particular feature as we go out into the modeling world. So very simple rule here, again, creating just those guys. And if we exit out of here and come back to our model, we can see again our feature living in the middle of that history right there. And I told you we'd do this. We can not edit the name. Let's come back here and we can crank up the resolution on this one a bit. Let's see. Let's go. We can kind of quadruple this. Let's go like 32 and maybe 16. I think we'll keep the aspect ratio the same for these guys. And as we do this here, this will take 15-20 seconds to update, right? But really, again, what it's doing is creating that hex pattern out there. Taking the hex curves, offsetting all of those inward, and then after all of those offsets inward, it's extruding all of those, and then uniting all of those here at the end. With our unite rule, we've chosen a feature bodies selection intent rule, and so that's going back to this feature, this algorithmic feature, and dynamically selecting all of the bodies that it creates. We were creating, I forgot what the number was just a minute ago, 23 or something like that, bodies before. We're going to create a lot more than that now. And that's okay. NX will associatively find those and update those. So I'll go ahead and poke this. And this, again, will take 15 seconds or so to update. But we'll get a much finer grid here of hexes on our mat out here that will hopefully help us slip a little bit less as we're standing at the sink, for instance. But yeah. There we go. And we've got now our new hexes all done. Our unite has a little warning on it there that the number of tool bodies has changed, which is accurate, right? It's letting us know that as it's performing its unite, that it's got more bodies now to deal with, and that's totally fine, right? So that's a real simple example, planar example of an out-of-the-box parameter, right? Out-of-the-box pattern, rather. A nice rectangular area. So that one's super easy. And so next, what I want to do is do a non-planar example, right? And this is that isogrid example that we're looking at with a nozzle just a second ago. So I'm going to go ahead and close this part here, and we can grab then this guy. So this one, as we mentioned just a second ago, really we start with a curve that's there, and revolve that guy, and we'll shell that, right? So that's kind of where we're starting, and at that point, then we're going to go and apply this algorithmic feature, right? This algorithmic feature is going to create a bunch of solids and things on there, and then I've got some offsets and some trimmings and things like that to kind of clean up the ends of this. That's how this model is put together, and the end result of this then is I believe, I think it's all united. Yeah, it's one big body. Yeah, there's my unite in there, right? Good. So this is this model, right? Let's look at the algorithmic feature for this, and there can be some similarities here to what we saw before, but this one's a non-planar example, right? And so, for instance, in this guy, you'll see that we have a similar face at the beginning. We've got a triangular grid this time. We're using kind of the individual sides of this to extrude in this case. Similar kind of count in U and V on this one. This one, the U is kind of along the axial direction here. So this 3 is corresponding to this kind of this axis right here, where you see 1, 2, 3 of the kind of the base leg of the triangle come in this direction, and the 6 is circumferential going around there, right? So we'll again crank this up in a minute. but yeah, from here, what we're doing is taking that triangular grid, putting some ribs out here that are based on all the lines that are coming from actually the curves, rather, sorry, that are coming from this. I'll point out the distinction in just a second there. And then putting some little cylindrical nodes out here at all the points that are coming from that triangular grid, and putting those at a face normal out there, right? So each of those is normal to the surface at its local point. And so with this little network here, right, we're able to create this set of a whole bunch of bodies, 71 ribs and 29 cylinders, right? So that's pretty close to 100, actually. I didn't realize that till this moment. But a bunch of bodies there that we're creating that are going to go to our output. Okay. Now, just for fun, I think this is a good example to just rebuild from scratch, right? And so what we can do actually here is, in the context of this feature, I'm just going to select everything and hit the delete key just for fun. And so we're still in algorithmic modeling here. We're still right in the middle of our model actually here. And what I want to do is just rebuild all of this here from scratch, and then we'll take a look at how that goes together. Okay, so here again, we started with that triangular grid. So if I start typing try, that gets me close. Try A gets me a little closer. We'll grab actually not the cell. I want the grid here because I want those individual edges. So I can just hit the delete key to delete that guy. And here again, creating the inputs for this, the easiest way is to just right click and choose create inputs there, and that'll start me off, right? I wanted to start this one just a little more. I know that 3 and 6 is a little better aspect ratio for the numbers here on this guy. Actually, just for fun, we'll leave those at 5 and 5 for a minute, and you can see the effect. But we'll select that face out there as our geometric input. And there's a little preview here that we can use to see what we get here. So we are starting with some curves, and you'll notice here that it's a little messy, right? And what we're really looking at here are, again, there's some lines that are joining those grid points. If we want to have straight lines between those, there's a picture, I think, that Mason had in a presentation of a kind of a structure, a twisting structure that was using those kind of straight lines. But we're not going to use those straight lines. We're going to use these curves, and the curves are the ones. If we switch, I'm going to send this to the output. That we've got some predicted nodes here, some AI to look at what you've done before with these. Sure enough, I've done some ribs recently, and so it's telling me that ribs may be a good thing to do with these, and I'm going to use that in just a minute. But if I can send those curves specifically to the output, these are the ones on the surface of this body, and these are the ones that I want to use, right? So I'm going to use those curves here in a minute to generate the ribs. Okay. In fact, let's go ahead and do that. Let's go to curves there, and I'm going to use that prediction to generate some ribs. So I can grab a node that way. If I wanted to come over here and I know I want to use ribs, I can type in rib and grab it over this way instead. But this works well, right? These ribs are the face for this. The reference face there is going to be this same one. So I can grab that same face and reuse that here for the rib. And the height and thickness here, I'm going to type those in. So there again, I can just use create inputs now. This will create the rest of them for me, which is nice. And I'm going to have these be 8 and 8 here. And here again, this is going to start to create those ribs. I can preview those if I want, but here I just want to send those to output. So I'm going to send those up here. I don't really need those curves as my output. I really want the solids up there. So I'm going to do this, and you'll notice the top connector is turning blue there, which tells me it's about to replace that one with this one. So this will send my ribs to my output, and that's great. As I do this here, I've noticed that the corners here are a little messy where everything's coming together. And so that cylindrical feature is, in all honesty, intended to kind of mow over the top of this and just make that simple, right? And so let's do that. I want to create that cylinder up, the cylinder node. And so let's start typing cylinder, and sure enough, we've got that guy. This one is similarly looking for some points for these. And again, these are going to go at all of these points here. So we'll connect that guy. The direction here is kind of interesting. Again, we want to find all the normals at these points out here. So again, I can start to type in, say, normal over here. And sure enough, right there near the top, I've got a face normal that'll create a normal to the face at a given point, right? So again, using our lists here, what we can do is say I want to use that face, and I want to do the normals for all of these points. So 39 points here, we'll feed it these 39 points, and the result here will be, we display data, will be a list of 39 normals, right? That are in the same order as the points that we had down here below. So with those points and those normals, we have the direction for our cylinders all figured out. And here again, let's create a diameter and a height. And I think those want to be about 20 and about 10, and that should do what we want to do. And here again, we'll take those bodies now and send those to the output, and we'll get all of these cylinders showing up out here. Okay. So this is kind of how we did it, right? That's the rule that we were looking at just a minute ago. We've recreated that one from scratch, and that's how that works, right? So now as we finish this will go back out into NX modeling. Again, it'll continue on the update history. One of the next steps there is to unite everything, and then again, it's going to kind of do a couple offsets and trim up the ends and so forth, and we'll see our finished nozzle there, and we'll say yes, let's save this and finish. Again, this is going to go out, do its thing, and continue its update, and we'll see that it successfully updates here momentarily. It creates really those 100 features, right? Those 100 ribs, and there's, what was it, 79 ribs and 21 cylinders or something like that. There we go. And this one's a little confused at the moment. Yeah, that's okay. We'll survive. Let's take a look at this here again. So, we're in 5 and 5. That's why we've got kind of a weird condition. If we look at this one, it's over in here, yeah, with an odd number coming around, we get kind of in a funky shape there. So what I want to do is change that to 3 and 6, and that'll look much better, and close up nicely at the seam there, and then everything will unite nicely here as well. So yeah, there we go, much better. And then yeah, we could come and take that and crank that up a bit here as well. So if we go to say 4 and 10, for instance, here, that'll add an additional row here axially, and add a few more coming around circumferentially here as well. And that again will take a little bit to update there, but then it's going to go and clean up the ends, and there's our little more complex one, which is pretty cool. So again, example there of doing that. Let's see, one last thing I wanted to do here just for fun was to take that, show the full thing. So we've got that curve right there, right? We could actually take that sketch curve if we want to and go all the way back to the beginning and say, I want that to be a little wider down in that region. And I want this to flare a little bit, say coming there, right? And change the shape of the whole initial body that this is based on down there. And that's totally fine, right? We'll do that. And as we finish this curve, again, we'll see the entire shape of that nozzle update. So again, these can live and participate very robustly in an extended parametric model, which is super, super exciting. So opens up some really fun doors here to create some shapes that would be relatively tricky to model, require some manual interaction, a lot more manual interaction in traditional NX modeling. Okay, so hopefully that kind of shows how the whole picture plugs together. Good. Let's see the next one. Two more really quickly. I wanted to show you. One is that airfoil, right? Let's go ahead and close this and let me grab the airfoil one. This particular one, I had a question about this, was really how to create a spline from, in this case, a comma separated values file here that is kind of a standard airfoil definition, right? So for instance, if I pull a folder over here, yeah, these are some standard CSV files here that have some common airfoils in them. And this particular one, let me bring this over here, looks just like this, right? We have a list of X, and Y, and Z coordinates out here. This is a kind of a standard format that kind of makes the chord length, initial chord length 1. So we can take these and scale them. But this particular one's got 130, I guess 129 points in it. And so we're going to do that one. I think this other one doesn't have nearly as many points, if I remember right. The NACA airfoil. Oh, yep, it's in a different Excel session. Here we go. So this guy, yeah, this guy's got 36, right? But again, one of the strengths of algorithmic modeling is that list processing, right? And so this particular one, what we're doing in the list, super, super easy. If we look at the definition of this, is we're selecting that CSV file. That's one of our standard inputs over there. We're reading that table and kind of splitting that up into its rows and then really feeding the X, Y, and Z values into creating some points out there. The points we're not sending to the output. They're just construction geometry, but those points become input points for a spline. And in this case, we're doing a degree 2 spline, so nice and smooth, no inflections. And it's not a closed spline. The front first point and the end point happen to be the same, which gives us a nice pointy trailing edge. And doing this as a through point spline as opposed to a through poles down here, right? But anyway, that's simple rule. But the really cool thing that's happening here again is this associative connection to the CSV file that's out there on disk, right? And that's pretty exciting. So with that, let me just come back out of this here and we can see what this looks like. So this feature, again, living in here, there's an extrude, of course, downstream of that that's dependent on it. But as we edit this feature, it has us select a CSV file. So I can go out there and grab, for instance, let me get in the current one that we're looking at here, which is this guy. And this is the one that's on the screen right now, this NACA airfoil. I'm going to grab this RAE one here. And this right now, let's see, actually, let me back out just a little bit so we can see the difference. This one's a very, very smooth kind of normal shape airfoil, right? NACA 4-digit airfoil, super, super simple. And what we can do then is this other one is a very different kind of shape. Not super, super different. It's still an airfoil, right? But this guy here, again, we're going from 40-ish points to 120 points. It's totally fine, right? The feature doesn't mind that at all. There we go. And this is the different shape here, right? So again, we're dynamically reading that set of points from disk, going out, creating this spline. It's replacing that spline, of course, because the downstream features here are successfully updating. But another just kind of simple example, right, of a thing where the list processing helps, that dynamic number of things helps, that associative connection out to the CSV file really helps here. So anyway, useful case for this kind of modeling. Last one really quickly is a speaker grill example that we got to do a speaker. And some of you may have seen this one as well. I do have a YouTube channel out there with a bunch of stuff, and this is one of the examples that's out there. But wanted to make the point here that we can take those rules that we've created and we can save those into the reuse library, actually, right? And so those can become then a feature that sits out here that we can drag and drop, for instance, and add to this model. We also can take those if it's a useful one, and we can say, for instance, that I want to add this to the home ribbon tab here, for instance, right? And this is going to create up here on my ribbon tab a button for this one, right? So that feature now looks like a feature, and I can launch it from a button that's on my ribbon tab, just like any other feature out there, and start it this way if I want to, right? Or again, drag and drop it in here, either one of those, right? And again, launch a dialog that looks familiar. This one needs a face and a body as an input here, so I'll select those, and this is going to create here this phylotactic spiral, which is a cool shape here. This is phyllotaxis is talking about like the arrangement of leaves on plant stems, right? And there's a whole set of science around that. So this example here, yeah, again, is placing a whole bunch of those, again, based on an interesting algorithm that's in here. We can crank that up. I wanted to show here very quickly that we can go, say, let's go 700 here, right? Actually, let's back up. If we come back here one step and we look at the faces here, we've got about 90 faces right now in this, particularly with all the Siemens logo stuff in there, right? And as we come to this one, as we look at those faces, we've got, where are we? 456. So we've got, in the neighborhood of 300 and 340, 360 holes here, right? That we've created very, very quickly. And I want to roughly double that here just for fun, right? Let's go to 700 here on this side. These are going to be big holes. We'll see how this diameter factor works here in just a second. So this will create lots and lots of holes that are going to overlap with each other, and which is that one. And we're going to fix a couple things. Let me do this version. This is a kind of a denominator for figuring out the size of those. So I'm gonna half the size of the holes here. Some of these are overlapping in the center, so I'm going to make a little more room in the center there. But this again is creating in the neighborhood of 650 or so holes in this guy, right? As we look at the faces here again, we're at 841, so yeah, 750 holes, right? In this case, and you saw that just took a couple seconds to do that, right? So again, really powerful ability to do large quantities of these kinds of things very quickly when we want to. Okay. So that's I think the stuff that I wanted to show you there. Let me jump back over really quickly to here. Yep, that's the one. And with that, in the presentation, I'm happy to share the presentation out there. There's one kind of text example here that kind of walks through kind of how to build some of these, or how the nodes may go together. That you can look at for reference. There's some tips and tricks in here as well, a few of those that I've thrown into this presentation just to have those be available for you. And you can refer to those later when you start diving in. And last thing I wanted to mention is licensing for this. This is an add-on module that we have for NX. So there's a product number here, this NX 30801, that ATA can help you with if you'd like to. And this is also available through our value-based licensing pool, or our token pool out there as well. So if you've made the jump and are starting to use our tokens, super flexible way to try really any of our add-on modules with no trial licenses or things like that, and to very flexibly use the stuff that is useful to you, particularly for infrequent usage or less frequent usage, right? To be able to jump from module to module or add-on to add-on very, very flexibly throughout the day. As we describe our token system, it's like going to the arcade with a quarter that, and as you play games at the arcade, the quarter, you finish the game, the quarter comes back. You can take that quarter and use it in the next machine immediately. So we don't consume those tokens, we let you reuse those, and so super flexible way to get at NX. So with that, yeah, I think that's what I wanted to show. We've got roughly a little less than 10 minutes. We were close. And so, yeah, if there are any questions or comments or complaints or confessions at this point, I'd love to answer those.
Thanks, Taylor.
You bet.
I love the quarter and the machine analogy. Love it. I don't see any questions so far from the chat. If you have any questions,
looks quiet.
Type it in, or if you want to ask Taylor directly, we can unmute you.
Looking quiet. Hopefully people are still there. All right.
Yeah, we'll get this video posted online in our ATA YouTube later on, in case people want to rewatch it and know some of the tricks again. All right. I don't see any questions, Taylor, so I think we'll let you go early.
No problem at all.
Appreciate your support. Yeah, let's end this here and hopefully get you online next time.
Very good. Thank you all for attending. It's great to have you with us. Yeah, and feel free to contact me if you have questions.
Thank you, Taylor.
Okay, thanks much.
Nice.